Okay, this will be the lecture for Chapter 16, and we'll be now talking about, well, how do we actually go ahead and transfer heat from one object to another one. So what we're going to talk about is going to be the three methods of heat transfer: conduction, convection, and radiation. We'll also talk about Newton's law of cooling, which is ironically also going to apply to warming as well. And then we'll talk about how this thing called radiation is going to affect Earth, affect its climate, and how greenhouses work, whether we're talking about while your car is hot in the summertime, or how greenhouse gases can affect Earth's climate in general. Now, just kind of a brief overview of these three methods of heat transfer, or the transfer of thermal energy. First of all, let's keep in mind that it's always going to flow from hot to cold. It's never going to spontaneously flow from cold to hot, so this is definitely not going to happen. And if we think about having our house at 20 degrees Celsius, and maybe it's freezing outside, so 0 degrees Celsius, then this is kind of going to be you and your house. Then heat's going to flow in this direction right there, and it's going to do so in three ways. First of all, there's going to be conduction, and for conduction there has to be some physical touch. So if you looked at the window of your house, then right over here there's some places where the glass is going to touch the air, and it's going to conduct some of that heat outside of your house. Then what's going to happen is going to be convection, and essentially what convection says is hot air rises. So here we've got some little chunks of hot air that bounced up against the window and touched it, and these guys are going to naturally tend to rise, and they're going to take heat away from the house. And last but not least, there's going to be this form of heat transfer called radiation, which is essentially going to be energy and light. So just like the sun warms us up, your house is going to be radiating some light, and it's not going to be a color that we can see, but it does radiate it, and it's going to essentially take some energy away from your house. So let's go into detail into each three of these methods. First, let's talk about conduction. And conduction, the important thing is going to be there has to be some physical touch. And if you think about having my proverbial poker in the fire, then what's going to happen is heat's going to flow from hot to cold, and the hot end is going to look like this, the cold end is going to look like this. And let's just say for a second this is going to be a copper poker. And so here's my fire, and here we have a whole bunch of copper ions, so keep in mind that these guys have a net positive charge, and what they kind of have is a deficiency of electrons. Well, two things are going to happen. First of all, these guys are going to start to wiggle a lot faster, and it's going to bump into this one, that one's going to bump into this one, that one's going to bump into this one, and this one, and kind of and so on and so forth. And so these guys are bumping into one another, and they're also kind of passing electrons around. So this one's going to pass an electron to this one, it's going to pass it to this one, it's going to pass it to this one, pass it to this one, and those electrons are actually going to carry some heat energy as well. Now, you may be asking yourself, well, why does this thing have a plastic handle or a wooden handle, or why do pots and pans have them? Turns out that different objects are going to conduct heat kind of differently. So this kind of leads us into this idea of thermal conductivity, or how well does an object conduct heat? How well does it move heat from one end of it to the other end of it? And it turns out that there's going to be two types of objects that we can talk about. We can talk about things that are conductors, or things that are insulators, and probably not surprisingly, conductors are going to conduct heat very well. Insulators are going to insulate very well. They're not going to conduct heat very well. Now, how do these things go about conducting heat? Well, first of all, yes, the atoms are going to jiggle and they're going to bounce into one another, but keep in mind that it's great to kind of conceptualize, but this isn't actually the primary transfer mechanism. It turns out that the electrons are what carry most of the heat, and it's going to be very fast transfer. Probably not surprisingly, objects that conduct heat very well are also very good at conducting electricity, so think things like metal. Insulators, on the other hand, well, insulators tend not to have this free electron that conductors have. Sure, the atoms are going to jiggle against one another, but it's going to be a relatively slow transfer of energy. So think of things that are not good conductors of electricity. Think about things like wood or plastic, or actually, believe it or not, air. It turns out that good insulators are poor conductors, and vice versa. Now, I have a little demo for you. I'll let you watch that real quick. Now, why doesn't the piece of paper catch on fire? So this is going to be my proverbial, flame, if you will. And, let's kind of have this piece of paper up against the metal. Well, it turns out this metal has a whole bunch of free electrons, and these free electrons can, carry this energy away. So yes, while it does get relatively hot right over there, and this guy takes that energy and runs over here with it, this guy takes that energy and runs over here with it, runs over here, and runs over here, and it turns out the paper is just not going to catch on fire. Why is this? It's because this metal right here is a good conductor of electricity and heat. Now, I want you to take a second and read this question and think about it really good, because it's actually a little trickier than you might think. So, now I trust that you've read it and thought about it, and heck, maybe even made a choice. So what can we say about the temperature of the tile? Maybe kind of surprising, but the answer to this one is going to be this one right over here. What I want you to do is, pause this for a second and get yourself a real glass and a plastic glass, or even better, a styrofoam glass. So it's going to have two cups right over here. This one's going to be styrofoam and this one's going to be glass. And I want you to go ahead and grab hold of each one of these and ask yourself which one is colder. And you're probably going to say, well, this one is colder and this one is going to be warmer. But what would happen if I put an ice cube in the bottom of each one of these? Well, if you said that this one right over here is warmer, then it should melt the ice cube faster. But we typically tend to buy styrofoam coolers, so this one should be, should be colder, perhaps. Now, it turns out that these two cups are actually at the same exact temperature because they've probably been sitting in your house like forever. The same is true for this tile. It's been 80 degrees Fahrenheit all morning, and the carpet is at the same temperature as the bathroom tile. However, the difference between the two of these is the tile is going to conduct the heat away from you a lot faster than the carpet is. The same can be said about this glass and this piece of styrofoam. This guy is going to be a good insulator. This guy is going to conduct heat very well, and that's why the glass feels colder, even though they're both at the same temperature. This idea of thermal conductivity kind of explains why people can put their feet to the fire, so to speak. If you think about it, this fire looks really hot. But if you go ahead and you see firewalkers, they go and they walk across these coals, and I may know the physics behind it. I still think they're crazy. Now, it turns out that this ash right at the very tippy top of the hot fire is going to be a relatively poor conductor, and even though this fire is going to be relatively hot, then as long as the conductivity is poor and you touch it very briefly, then you can go and walk across some coals. Reason behind it: poor thermal conductivity. Now, one day perhaps you're going to buy a house, and then all of a sudden you're going to care a lot about trying to reduce these conductive losses inside of your house. So if you look at a thermal picture for a house on top and this house on the bottom, what makes the difference between these two guys? Well, this top one is going to be well insulated, this bottom one is going to be poorly insulated. And especially look around the windows, right over here, right over there, by the door, and by the door. This house right over here probably has double pane windows, or something similar, which are really good at reducing these convective losses. Right up here, there's probably a whole lot of insulation. We know that heat is going to rise, and you can kind of see that. You can kind of see in this house right over here that there's a lot of heat coming out of this top window right here. So this house has got some really good thick insulation in it. This house right over here was probably built in like the 80s, when you didn't have to have nearly as much insulation. So reducing conductive losses, insulate your house. Now, kind of the last example I want to talk about for reducing conductive losses is actually going to be fluffing, why birds kind of fluff up in the winter. So you got this bird right over here, and you see it in the wintertime, it's going to say, "Birds, cold out, I'm going to fluff up my feathers." Well, this is actually kind of like us putting on a down jacket, if you think about it. Down jacket's really warm. Now, what do? It turns out that they're really good insulators, and what the bird is actually doing is it's actually putting a whole bunch of air around it. And air is a really good insulator, and it's going to essentially reduce the conductive losses for this bird. So good insulators, air, feathers, wood, snow, believe it or not, and hot coals. The last thought I want to leave you with as you go ahead and insulate your house is that it's not going to prevent the flow of energy from hot to cold. Nothing can prevent the inevitable flow of this energy. All it's really doing is it's slowing it down. If you add more insulation, then it's going to slow it down. It's not going to totally stop this flow